Okay, well, thanks a lot. So I will give this lecture in English because there are many international people in the audience, and well, science is international, and it's easier this way. So I will talk on ultimate Rayleigh-Bénard and Taylor-Couette turbulence. But first of all, I would like to thank you again. So thanks to the Deutsche Physikalische Gesellschaft, thanks to all my teachers, colleagues, postdocs, and students with whom I had the privilege to learn from and to work with. And well, as past pro todo, I would like to name three. First of all, Professor Siegfried Grossmann, my PhD advisor, from whom I learned tremendously. And then Professor Leo Karanov, my postdoctoral advisor from Chicago, and my friend and colleague, Professor Andrea Prosperetti from Johns Hopkins, from whom I also learned tremendously. And of course, I would like to thank my Physics of Fluids group at University of Twente for now more than 20 years of very close interaction and collaboration. So on this particular subject, there are various co-workers and colleagues and funding, and you see a color code here, and I will show you what is the motivation for this color code at the end of this lecture. So I will talk on what I call the Drosophila of physics of fluids. And these are these two systems, a Rayleigh-Bénard system, a container heated from below and cooled from above, where heat is transferred. And then the Taylor-Couette system, these are two coaxial cylinders with liquid in between, and angular velocity is transferred from the inner to the outer cylinder. And what makes these systems so nice is that these are closed systems, and therefore you have global balances, which as a theoretical physicist you of course love, and they're mathematically well defined. So Fritz Busse from University of Bayreuth has called these two systems the twins of turbulence research when discussing two articles here. So for me, these are ideal systems to study the interaction between the boundary layer and the bulk of turbulence. And to illustrate the objectives, the scientific objectives, I show you here again this Rayleigh-Bénard system with Rayleigh and Bénard, two of the heroes well, Rayleigh, one of the heroes of theoretical physics. And well, you see the gravity field, the height, and then the temperature difference. And it's of course of tremendous relevance in various contexts. It's of relevance for, in fact, the current in the ocean here. It's of relevance inside the Earth. It's of relevance for the atmosphere, or even in astrophysics or in industrial processes. And the questions to ask is, what is the heat transfer? The heat transfer from the tropical ocean to the northern ocean, heat transfer from the core of the Earth to outside. And the question, of course, is how to upscale things. So we have this little experiment, this flow in a box, how to upscale this to this much, much larger scales. So you need a deep physical understanding of what's going on. So here I show you in a log-log plot the heat transfer versus the temperature difference, and there's a classical scaling law. So in physics of fluids, people want to express this in terms of scaling laws. So Nusselt is the heat transfer, and Rayleigh is this dimensionless temperature difference. And there's a scaling law which had been suggested back in 1954 by Malthus. This says that Nusselt goes like Rayleigh to the 1/3. And well, then you extrapolate from small scale experiments to the real thing here, say the heat transfer in the Earth. But this can only work once there is no transition. However, there may be a transition, and then, in fact, an extrapolation along this line will lead to a very, very wrong result. In fact, there may be huge differences in the heat transfer, whether you know about this transition or not, And that's why we would like to understand what's going on. What's the nature of this transition? Can we understand this? And well, here I define you this problem, this Rayleigh-Bénard problem. Container heated from below and cooled from above. It's characterized by the height L, and it's characterized by the material properties, which are the kinematic viscosity, the thermal expansion coefficient, beta, and in fact, the thermal diffusivity kappa. And they are assumed to be independent. And hot stuff will go up because the density of hot stuff will be lower. And here you see the temperature dependence of the density. It is this density difference which drives this flow and leads to this convection row here, which is called the wind of turbulence, large-scale convection row. Well, as a good theoretical physicist, I must show equations, but there won't be too many. This will be pretty much the only one. And I'll show you basically the Navier-Stokes equation or an extension thereof, which is called Boussinesq equations, which you see here. Basically, it is the balance of momentum, and it is learned by students in the first year. Here you see the heat transfer equation and the incompressibility here, and you have the property boundary conditions that the velocity is 0 at all walls, and the given temperature is shown here. What are the dimensionless parameters governing these equations? And well, you make this dimensionless, and what you get as dimensionless parameter is the Rayleigh number, which I showed you before. It's basically the dimensionless temperature difference, and then it's a Prandtl number, which is a material property, and it's the aspect ratio. It's a geometrical ratio between the width and the height. And here you see the flow from a numerical simulation, and you already see the many scales which occur here. So small scales detach here and drives this flow, and this leads to heat transfer. So red stuff is hot, blue stuff is cold, and the heat is transferred here. The big question now is, what is the global response of the system to these control parameters? So how does Nusselt, so heat transfer, depend on Rayleigh, Prandtl, and gamma? And how does Reynolds, which is a measure for the intensity of the turbulence, how does it depend on this? So you see, it's a Reynolds number, and this is the intensity of the turbulence. And here I show you what's going on. Here you see the hot stuff going up, the cold stuff going down, driving the flow. And what's particularly fascinating is that out of the small-scale structures, these big structures develop, and this role of convection. And this is a numerical simulation. It's very demanding to do these numerical simulations because so many different scales have to be resolved. So here you see again how the driving works, plumes detach and drives this flow. And well, how to do this? And it's only possible thanks to PRAISE grants. PRAISE is also a European facility to do high-performance computing. Without this, it wouldn't be possible. And in fact, this calculation is done partially in Switzerland, Germany, France, Italy, England, all over. So it's really a European effort to do that. And to give you an idea, one snapshot of the flow, which I showed you, is 1 terabyte. Right? It's really petaflop computing, and you must be very, very efficient in doing so. But you really solve the Navier-Stokes equation, and there's no modeling involved. It's massive parallel, so 10 to the 4 cores and more. And it has been done with my colleague Roberto Versico, but many, many extremely smart and hardworking PhD students and postdocs. So we developed this code, which is open access and free to use. And here you see what we applied it to the Rayleigh-Bénard convection. To double diffusive convection, this is a convection in the ocean, whereas not only the temperature field coupled, but also the salinity field, and to Taylor-Couette flow. Well, at least the designer of covers from Physical Review letters likes Rayleigh-Bénard convection quite a bit. So here you see rotating Rayleigh-Bénard, double diffusive convection, and ultimate Rayleigh-Bénard convection. And this gives me the opportunity to really stress how important the journals of the learned societies like Physical Review is. I mean, this open access is called open access in language of George Orwell, in Newspeak. In fact, it's pay to publish. And there are very many commercial publishers who want to make money and earn money. This is, in fact, a learned society. It's the analog to Deutsche Physikalische Gesellschaft for America. And it's in fact, a very good price for great quality. And it's a journal driven by the scientific community. And this is what we should keep. And well, I'm sure that Professor Meschel couldn't agree more on that. So it's also very important for the politicians to be aware of this. So what drives this so-called open access is pay to publish. So it's a commercial thing, right? And we want to drive it from the community. So well, back to the subject. So Nusselt and Reynolds in a so-called classical regime is being well understood. The physics and a good agreement between experiments, numerics, and theory. And here you see the huge range of parameter which can be achieved in Rayleigh number and in Prandtl number. And well, each data point is one particular experiment. And you see it covers 14 orders of magnitude in Rayleigh and more than 10 orders of magnitude in Prandtl. And well, we developed this unifying theory of thermal convection. And the result is that there's no pure scaling. So this Nusselt goes like Rayleigh to the 1/3 is not correct. In fact, what is the core of the theory here is that you must decompose the flow into a boundary layer, which you see here, and into a bulk. And this holds both for the kinematic part and for the thermal part. You see the plumes driving the flow. And then the energy dissipation in the boundary layer obeys different physics as compared to the energy dissipation in the bulk. And the total dissipation is the sum of both. And once you accept that the physics in the boundary layer and the bulk is different, in fact, pure scaling laws are off the table. I mean, that's really something one must realize. There is no pure power law, neither for Nusselt nor for Reynolds. And we can work this out, and we did. And here you see Nusselt compensated with Rayleigh to the 1/3 as function of Rayleigh and Prandtl in a log-log plot. If this Nusselt goes like Rayleigh to the 1/3 would hold, it would be a flat plateau, but clearly there's lots of structure which excellently describes all data around. And well, here you see a cross-section, Nusselt versus Rayleigh, also log-log. If it would be Rayleigh to the 1/3, it would be a flat line, but it isn't, and you see very good agreement between theory and the data. The same holds for the Reynolds number. Again, no scaling law. It's a smooth transition from one regime to the other with quite complicated structure. The crucial assumption which goes into the theory is that the boundary layers are of Prandtl-Blasius type. And here you see Prandtl and Blasius, and they developed this theory. And you all know that at some point when you drive the flow, it will no longer be laminar, but it will become turbulent. And well, how long is this the case for this flow? And well, there, as a good theoretical physicist, I consult Landau-Lifshitz, and Landau-Lifshitz claim, and that's about correct, is that the transition happens at a shear Reynolds number of about 420. And within our theory, we can, of course, calculate this. So the question is, at what Rayleigh number does this happen? So when do you have the transition from a laminar boundary layer to a turbulent boundary layer? And this is a boundary layer of the type Prandtl-von Karman. So Prandtl did both. With Blasius, he did the laminar boundary layer theory, and with von Karman, the turbulent boundary theory. And we can calculate it within the theory, and we get this line here. So beyond this line, in this pink regime, you have the transition towards ultimate turbulence, where you have a turbulent boundary layer. So we predicted back in 2001 that this transition should happen at Rayleigh 10 to the 14. It's very difficult to reach these experiments. You want, of course, to understand what do you expect in such a regime. And the first prediction for a regime where boundary layers are turbulent had been done by Bob Kreichnan. He predicted this behavior here, Bob Krajnan was, in fact, the last postdoc of Albert Einstein, and Albert Einstein had given him turbulence as a warm-up problem. So he was supposed to do general relativity and ground unification theory. So Krajnan is one of the great heroes of the turbulence research, but he always suffered that he couldn't resolve this. So this is a problem given by his postdoctoral advisor Albert Einstein, and he suffered quite a bit that he couldn't solve it and never came to general relativity and to quantum theory. But he had huge achievements and a wonderful theory, and well, Einstein in fact underestimated the difficulty of turbulence quite a bit. Well, what does it mean? It means an effective scaling law that Nusselt goes like Rayleigh to the 0.38. And well, we reformulated this here and found a different log dependence for the Nusselt number, but basically effectively also meaning Rayleigh to the 0.38. What you both mean this, Rayleigh to the 1/2 times log corrections. And what you see is that if once Rayleigh goes to infinity, then you get this pure scaling Nusselt goes like Rayleigh to the 1/2, and that we call asymptotic ultimate regime. And well, how to get there? An experiment. You see there's only one experiment which gets there, and that's an experiment by Günter Ahlers and Eberhard Bodenschatz, whom you see here in Göttingen. This is the so-called Göttingen U-boat here. This is an experiment with pressurized F at 6 at 20 bar. And what they achieve is, in fact, a Rayleigh number of 10 to the 15. And it is only this trick with this pressurized SF6 that they achieve that regime. So here you see, well, you may want to stay here then. So here you see the data, Nusselt compensated versus Rayleigh, and here you see the transition, right? The transition towards the ultimate regime here, and this slope indeed is 0.38 as we predicted. And that was measured in 2012, and of course we're very, very happy that this happened here. So how to extend this ultimate regime for a better understanding? And in fact, it turns out to drive Rayleigh-Bénard even harder is difficult, and therefore we switched to the twin brother of Rayleigh-Bénard, namely to Taylor-Couette, and as you see here, so in search for the ultimate regime in Taylor-Couette. So when you compare Rayleigh-Bénard and Taylor-Couette flow, there are many similarities. So here in Rayleigh-Bénard, you transfer heat through this large-scale convection roll, and in Taylor-Couette, in fact, you transfer momentum through these so-called Taylor rolls here. And you can build a one-to-one analogy between these two systems, Rayleigh-Bénard on the left and Taylor-Couette on the right. So here the driving is Rayleigh and the driving is called Taylor here. What's transported here is the heat flux, and we formulate this in the language of Rayleigh-Bénard right here. What's transported is the angular velocity flux, also expressed in terms of what I call a Nusselt number. And well, there are exact relations in both cases, and there is a scaling relation also in both relations. There is really a one-to-one mathematical analogy between these two systems. And here you see the parameter space. For Taylor-Couette flow, it's the inner cylinder and the outer cylinder, the Reynolds number, so how strong you drive them. And there are third parameter, there's a radius ratio between inner and outer radius. And here you see the Navier-Stokes equation for the case of Taylor-Couette. And it's good to transfer to another coordinate system here. So here you have complicated boundary conditions. So what we do is we in fact transfer these equations to the rotating frame in this frame of the outer cylinder. And well, as first-year student even, you know, then you get an extra force, and you get this Coriolis force here right now. So these boundary conditions here transfer to a Coriolis force by transferring of the coordinate systems. And when you now non-dimensionalize the equations, you get two dimensionless parameter. One is the shear Reynolds number, and one is what's called the inverse Rossby number for the strength of the rotation. Well, that we express to stress the analogy to Rayleigh-Bénard as Taylor number here. And So rather than having the parameter space of inner Reynolds number and outer Reynolds number to be in the Rayleigh-Bénard language and to learn from what we learned from Rayleigh-Bénard to transfer it to Taylor-Couette, we use this language here. And the question is now, what is Nusselt omega as function of Taylor and inverse Rossby? I mean, this is what physics is about, transfer insight from one area to another one. And it worked very, very nicely. Well, experimentally, this had been pretty unexplored. So here you see the parameter space, inner Reynolds number here, outer Reynolds number here, with co-rotation and counter-rotation on the right, respectively on the left. And there are very few experiments in 2010. Basically, the main experiments in the co- and counter-rotating regime are those by Wendt, also a PhD student from Prantl, and he did this, in fact, in Clausthal-Fellerfeld back in 1933. Yeah? And, well, to improve on this situation, we, in fact, built this device here, which we call Twente turbulent Taylor-Couette system. Well, it's a major device. In fact, it's probably one of the most turbulent flows under controlled conditions here. And many people of my group, also technicians, contributed to this. The parameter space which we can cover is shown here. Gives you some numbers. What I found is always the most impressive one is it's so strong driving that the liquid in between heats by 1 Kelvin per minute once we don't cool. So it's 20 kilowatt, is really a major machine, and we explore this parameter space here. For small Taylor-Couette, you see here a complicated parameter space, Reynolds inner, Reynolds outer, and well, for us, this now shrinks down to this little region, so it's down here, and we explore this whole parameter space to see what's going on in turbulent Taylor-Couette. So rather from being here, we go to this situation here. It's now filled with life. All data points are experiments and numerical simulations, and you really see that this area had a huge boost since 2010. We now get a good understanding of what's going on. So here you see a numerical simulation of what's going on for a turbulent Taylor-Couette flow. Here you see isosurfaces of azimuthal velocity close to the inner cylinder, and here's a zoom to the inner cylinder. And G.I. Taylor is watching this with great pleasure to see his Taylor rules here. So, and it helps, by the way, that you sit here. So you see the computer behaved. So it's very good. Yeah. Well, the overall behavior you see here, it's Nusselt versus Taylor. First, you have azimuthal rolls. Then you get Taylor rolls, and then you get this transition to the ultimate regime where the slope is 0.38. When you see the real data here, Nusselt compensated with Taylor to the 1/3 versus Rayleigh, you see the transition to the ultimate regime around 2 times 10 to the 8, so at a much lower number as compared to Rayleigh-Bénard, and here you have the ultimate regime with a much steeper slope. So blue is numerical simulations, and green is experiments. And well, we're very pleased to see this predicted exponent of 0.38 or 0.39 also in this system. What you also see is what I call the asymptotic ultimate regime is not yet achieved, but I will get there in a second. So how to achieve that? But before I do so, I want to really show that we really have the transition from the laminar boundary layer to a turbulent boundary layer at this 2 times 10 to the 8. And therefore, I look at the shear Reynolds number, which is shown here, versus Taylor. And well, I told you 420 is the number to remember from volume 5, Landau-Lifshitz, Theoretical Physics. And indeed, at 2 times 10 to the 8, you have this transition, and we are indeed in the ultimate regime right here. So we can also check that the boundary layers are indeed turbulent, and with their turbulence, they have a logarithmic profile. And here I plot the velocity versus the distance from the wall, and you see the straight line, meaning that you have a logarithmic profile right here. And that's checked here in experiments, and here in numerical simulations, beautiful log profile, meaning a turbulent boundary layer. So here you see the full phase diagrams. Good, so here's the phase diagram. And you see here the transition towards the ultimate regime. What you see here, this curve, is the ultimate regime which has optimal transport. So these are those data points. And remarkably, it's not here where you have pure inner Reynolds, inner rotation, but for slight counter rotation, you got the optimum transport right here, optimum Taylor-Couette. And well, this is also seen in the data here. So the Nusselt is largest for slight counter rotation. And well, that can be understood from these kind of plots. So what I show you here is the velocity profile here for co-rotation, here for strong counter rotation, where you get stabilization from the outer cylinder. But right here, you see these Taylor rolls, and these Taylor rolls help very much to transfer the momentum. And this means that you have a very flat profile. So here, for the case of slight counter rotation, you have a flat profile, and a flat profile means that the plumes enter into the bulk with the highest energy, whereas when you have a gradient here, the driving is not so strong. So really, a flat profile is connected with optimum transport. And well, here you see again the parameter space, ultimate regime up here. If you express this in the language of Reynolds inner versus Reynolds outer, is out here. And the old phase diagram of Harry Sweeney and co-workers is really down to that point. So even on a log-log plot, you see it's here, and you see this huge phase diagram of which we now have a very, very good understanding. And well, this is summarized here in this annual review of fluid mechanics on high Reynolds number Taylor-Couette flow. And here you see the comparison between Rayleigh-Bénard with the transition towards ultimate turbulence around 10 to the 14, and Taylor-Couette with the transition towards turbulence at 2 times 10 to the 8. So the mechanical driving in Taylor-Couette is simply more efficient than the thermal driving in Rayleigh-Bénard. From application point of view, what is in fact also equally important is pipe flow. So Taylor-Couette and Rayleigh-Bénard they are twins, but they have another older sibling, and this is pipe flow. And pipe flow is, of course, of tremendous importance for applications, pipelines, and so on. And when you compare Taylor-Couette and pipe flow, you can also put this in the same language. So in pipe flow, you have a pressure gradient, which drives the flow, and you have a friction factor, and you can cast that also in the language of Rayleigh-Bénard and Taylor-Couette. Here I show you pipe flow from Princeton. It's a huge controlled experiment, 34 meters in extension. Well, they can do this in US, but well, in Europe we are a small scale. We have to be smart, and Taylor and Couette, in fact, rolled up the pipe flow. So it's less space, it's less power. You don't have any spatial gradients, so you have closed systems, and also from physics point of view, you get extra control parameter, namely Reynolds inner, Reynolds outer, and this ratio here. So it's really good to explore the physics, which is the same in pipe flow, but there it's more hidden and more complicated to achieve. So here you see also the Taylor rolls, and here also rolls, and the analogy between pipe flow and Taylor-Couette flow, which you can also express in equations. So friction factor for pipe flow, you can have a friction factor also for Taylor-Couette, and when you cast this in Rayleigh-Bénard language, you have again the Nusselt number here also for the pipe flow. Well, one of the most famous experiments is the experiment by Nikoratske on rough pipes. So roughness plays a major role in friction. You have rough pipes, and here's the friction factor versus Reynolds for increasing roughness, and you see this plateau here and the increased roughness by Nikoratske. And the question is, what's going on Taylor-Couette flow? Can we measure this also, this increase, and also this flat plateau? So how does this friction factor behave for large Reynolds number for Taylor-Couette system, and can we achieve this asymptotic ultimate regime? And therefore, we tried to put in roughness into our device, which you see here, and we put in riblets in a controlled way, and we compare the cases for both walls being smooth, both walls being rough, and then only inner rough cylinder, only outer rough cylinder. And we did this both in experiment and in the numerics with both specific advantages. So in experiments, you can run the experiment longer, but you don't have full control on the velocity field. And DNS, you really can look into the flow in great detail. So things are complementary, and we did both. And well, here you see pictures from the smooth case and the rough case to give you an idea on the flow. You see much more intensity on this case here. And well, Nusselt versus Taylor, this I showed you before. Effective scaling, Nusselt goes like Rayleigh to the 0.38. On the left, the numerics. On the right, the experiments. You see there's still a gap, not completely overlapping, but clearly the same physics. But when we now, and this is the physics of this ultimate regime, but when we now increase the roughness, and I will only go to this case rough, you see that up here we get this regime, Nusselt goes like Taylor to the 1/2. And this is indeed what I call the asymptotic ultimate regime, which we achieved in this way. And I will show you how to achieve that. But first I express this also in terms of the friction factor. And in terms of the friction factor, you see it's independent of Reynolds number here. And well, we understand this in great detail. We did so by playing with parameters. As a physicist, you always want control parameters. And the control parameters here is the height of the roughness, the sparseness of the roughness. So S is this distance and H the height. And well, so the number of these blades which we put in here, of the riblets. And when you see, when you increase the height, you increase the overall friction. But in all cases, you have this flat regime, this asymptotic ultimate regime. And here you see the effective coefficient as a function of the sparseness. So here is very sparse, and here is not sparse at all. And you see there's an optimum in between. Optimum spacing, so optimum sparseness. And we understand this from, in fact, looking at the flow, and I have sketches here. So if you're too sparse, you have this obstacle, well, it's dominated by viscous drag here. The pressure drag right here is only very locally. If you're too dense with your riblets, you have a situation like this, and then again, dominance by viscous drag. No optimum, but in between you have optimum. And then, in fact, the pressure drag, so the flow hitting these obstacles is a dominant force. And this causes this asymptotic ultimate regime. This is also you see here. So we have the viscous drag and the pressure drag, and the pressure drag is this curve here. And you see for optimum sparseness, it's basically all pressure drag. So the overall conclusion is, well, Rayleigh-Bénard and Taylor-Couette are beautiful systems to understand turbulence, interaction between bulk and boundary layer. Here you see the experiments on the top and the numerical simulations on the bottom. You can do things more complicated. So what's very, very relevant is turbulent two-phase flow. You can add bubbles, and this I did here for turbulence in experiments, bubbly Taylor-Couette, and also in the numerics. And out of this, one can also learn quite a bit. And so once I think with the final slide, I would like to close with this. Here you see the color coding again. So the color coding is blue is experiment, blue like water, and black is numerics, black like silicon, and pink is theory. And with this, I would like to close and thank you for your attention, and I'm happy to take questions.